Okay. Hello, everybody, again. My name is George Markomanolis, and in this presentation, I'm going to talk to you about Rocprof profiling tool. I expect that the people who have used AMD GPUs a bit, they have heard it, and even they know it a bit. So many people contributed to the slides that we keep improving. Now, what about this tool? Roc Profiler, or simply Rocprof, okay, is a command line front end for AMD GPU profiling libraries. You can find it there as open source. Rocprof contains a central components allowing the collection of application tracing and counter collection. It's under constant development, so there's new releases quite often. And it's provided in the ROCm releases. So when you have ROCm, you have Rocprof also. And the output of Rocprof can be visualized using the Chrome browser with Perfetto, which this is the web address that we'll mention later, how to visualize it. Now, Rocprof has a few options, flags. Okay. So I have here an example from a bit from ROCm 5.2.0. Rocprof is here, and dash H is to show you the arguments. So if you click the timestamp, the option on and off keeps the GPU kernel timestamps. It's useful to measure the timing, etc. The base names is truncating the GPU kernel name. So if you have like template parameters and makes it the name of the kernel huge and base trace, you can activate this and have only the kernel name without extra letters. The dash O is about the CSV file, where to have some information about the counters that we'll see. Dash D is the data directory, send profiling data to a particular directory. And dash D is temporary directory, change the directory where the data files typically created in TMP, usually are in /TMP. I haven't used this overall because I didn't have any issue. But if there is an issue that you cannot create files there, you can change it to create a temporary file somewhere else. And then you have input files, okay, with some information in TXT or in XML. We'll see something about this. Profile the HSA trace. HSA is a command that our command is translated to HSA, so it talks to the GPU, right? The heap is the heap malloc, heap copy to instrument. ROCtx trace. Basically, this one is to have the API. I want to submit from here till here, and I name it this, so you can make it like custom tracing, not just a command or a routine or something like that. And KFT trace that I don't use it is to trace GPU driver codes. Now, this maybe the KFT and HSA can be useful when something is weird on one GPU or with a driver or something else, and you want to see what takes more time, etc. Now, there is also the -m metric file, allows you to define and collect custom metrics. And you can see it in the Roc Profiler directory or on GitHub for examples. Now, Rocprof can collect a variety of trace events and generate timelines in JSON format for use with Perfetto currently. So to submit a heap is a heap trace. To submit GPU kernels, you need to activate the heap trace. Hosted device memory copies, you need heap trace. HSA calls clearly HSA, and user code markers is ROCtx trace. And you can combine heap and HSA, right? And other things. So with Roc Profiler, here I give you an examples. I put the stats, the stats base names on if the kernel is strange and the application. So this is how you run it. You don't need to give full path because Rocprof is usually in your path, okay? And this will output two CSV files, one with information per each call of the kernels called results.csv, and one with statistics grouped by each kernel with results.stats.csv. So in this example, I think it's something like Jacobi. the content of the results.stat.csv is the name of the kernel, or as you see here, how many times they are called, each of them, okay? The total duration, but total duration is nanoseconds, but it's for all of these calls, average duration, and percentage that take this kernel in the total execution. So for example, if you have a slow kernel, but takes the 0.000% of the application, you don't care really to go to try to tune it. You care to go to see what is the bigger kernels, for example. Of course, can be something smaller, but still slow, right? So that's when it's extra to check it. This way, you know directly which kernels consume most of the time. It doesn't mean that the performance is low for now, right? That gives us the time information. Now, I do this heap trace, HSA trace, okay? And it will create a JSON file, okay? Then I copy this file on my laptop because we don't have a Chrome browser, I believe so at least. And I go to this website, ui.perfecto.dev. Okay, if you use Rocprof all the times, we're recommending the Chrome tracing, but now it's not that good as the Perfetto. Now you go here to this ROCm trace file, you load the JSON, and you start seeing this information. Now, as you understand, the x-axis is the time, okay? And then you need to expand this arrow, see more information, but you start seeing some workload, etc. And as we open, we can start seeing some information. Just to mention here, I thought it was here already. Yes, strange, I think I had it. The W is to zoom in, S zoom out, A move left, and D move right. So you use keystrokes, and it's really accurate compared to the mouse, I would say. So here you see a lot of lines because it's different, not different, it's same color, it's same type of event. But if you zoom, you will see start opening and opening and opening. And you see here the heap, okay, that we use, heap memset, and the GPU HSA API here. The screen doesn't fit everything. And I go and I zoom even further, and I see here down, you see the kernel. Here's Jacob iteration kernel with the options. And when I click to the kernel, you see the flow from what caused this. Here, for example, is the heap large kernel, for example, or HSA large something. Sorry, here's HSA. So activate to start run the kernel. So this way you can see, and of course, the x-axis is the time. So if you see a kernel take a longer time than the next iteration, while the problem size is the same, you can start saying, oh, this takes more time than the previous or the next. So maybe it's something I need to check, for example. And if I click here that I have the cycle, you can see information like this kernel, start time, duration, okay, was process, and basically begins. This is the begins and durations and end. And the flow event is that the incoming HSA dispatch. So this is here. This is the from HSA here is the HSA dispatch, okay, and it's the category data flow is a dependency and dispatch the kernel basically. So you can have a lot of information, and just to mention, I click here, okay, and opens this one, the top current selection, and when I click flow events, is here the flow events, okay. Now collecting application traces with markers. So imagine on the left, I have, this is a real code, and I say rock tracer mark, and I write something before heap large kernel, and I call that like that, and start heap large kernel range, the range start, and then push it, then call the kernel, and that says after heap large kernel, and this is to call it after heap. And then you can see before, so you can see your words in the visualization, so to know exactly which point it is. In case that doesn't provide enough information, you not go really specifically, I want to go around this code and start seeing what's the problem, for example. So, and in order to have this, you do heap trace and ROCtx trace, okay? So you do both of these. And then the application, the binary, and any argument you have. It's quite, I would say, simple. There's a lot of documentation, of course, in order to see what to do. Now, Rocprof does also hardware counters, and you can collect a number of hardware counters and derived counters, and you can see the availability with these commands. Just to mention, you have to be on the GPU when you run this stuff. And you can specify counters in a counter file. So if I want to use a specific counters, I do -I and a TXT file at the application, which my TXT file has this. This is an example, right? It's not mandatory. Each line, PMC, means that it will do 3 runs to finish the execution. And there is some counters that we think that many of them are nice to have information. And as you know, a limited number of counters can be collected during specific parts of the code, and that's why you can collect all of them in one run. And a CSV file will be created by this command containing all the requested counters. And also it's included also in the exercise. And now some of them, sorry, I go back and you see here some of the counters, the names, and here I describe, and I'm not need to read all of it, what it is each one. But the most important that if there's this XML here, but there's XML file in the Rocprof installation which explains its counter, what it is. And also, I like usually the one that says, oh, if it's close to 100% is good, if it's much less is also good, etc. The percentages, etc. is really nice to know, okay, I see a value, how know it's good or not, for example. So there's a lot of information that you can take from the counters. Now, counters, tips and tricks. GPU hardware counters are global. Kernel dispatches are serialized to ensure that only one dispatch is ever in flight. So this is a restriction that when we do with the counters. It's recommended that no other applications are running that use the GPU while collecting performance counters. So I'm trying to, I expect that this is per GCD, so I suppose it could be okay for exercises. Use base names on, which will report only kernel names, leaving off kernel arguments. And how you do the kernel duration, you do timestamp on and Rocprof counters and application, and then you will see this information when it begins and ends the kernels and complete nanoseconds. So closest thing to the kernel duration is these things. But if you run the stats that I showed you before, there'll be included a column that calculates kernel duration. And the duration is aggregated over repeated calls to the same kernel, right? For the statistics stuff. Now, the MPI ranks, it is possible to take this information per API process. It is a bit more, not complicated, but needs some procedure. So to debug the profile by executing an MPI exec heap trace Jacobi, this is a recap for Jacobi, or srun. This will produce a single CSV file per MPI process. Multi-node profiling currently isn't supported, but how we need some scripts to make it. So let's go first here. This script this is classic, I would say, script. Okay, two GPUs, etc. But here in srun, I call a wrapper. Okay, a Rocprof wrapper, a script. Okay, and Rocprof wrapper is in the next page. This is for a specific example that can be adjusted depending on what is the options of the application. Okay, so it's not the so in the wrapper you have if it's Open API, the API rank is this. If it's a MP or whatever. Now because you have SLARM, our API rank is this one. Okay, so here I'm taking the process number to make it separate for each CSV file, and you say the output directory is outdir. Outdir is the first option of this file. Of course, you can change it as you wish, right? This is just the name is the second argument. So the out file is the name, the process ID, and API rank CSV. This way, you create also a directory per API rank with its files what's there. And here, of course, the Rocprof, the output directory, HSA trace, where to save it, the out file, which the out file is this name, etc. And this is the rest of the arguments that you will put here. Okay, this is the rest of the arguments. So here, yes, okay. So this is how to do it in order to take one file per API process for CSV in the data files. So now about profiling overhead. As with every profiling tool, right, that collects data, there is an overhead. The percentage of the overhead depends on many aspects. You know that it depends. If you try to instrument something in a loop, and you do a million of loops, and you want to instrument each loop separate, etc. This takes a lot of time, and this is not only for Rocprof, it's for any tool. Also, if a lot of markers, that will define your own areas are added, especially in a loop, then it will take time. Okay, so that's why if you always compare the execution time before and after profiling and see if it's extremely different, then you need to try to tune it to have less overhead, because otherwise the data that you watch, especially for timing, is not accurate compared to the real application. In general, more data you collect, more the overhead it can be, and it depends always on the application. Yeah, correct. I was thinking, how can fail? So copy the mini, yeah, because I tried only from the other installation and I didn't try to copy only this. And yeah, so this one will start running many cases like that, while I have, although, yes, I try to do only one because it takes time. So it's a 655. The 6 doesn't matter this, doesn't matter this. Okay, so that's like that.
If it's important that we see what you're doing, can you zoom in a little bit to the terminal?
Sure. I mean, so if you see the instructions, when I do cut the heap and body org, I say that, can you see now?
Yeah, it's better.
So basically, I just commented the loop, okay, and I put one option because it just take time. I put like 65,000 options. And now I'm saying again from HackMD, the command is there, I mean, and I do this. Okay, so I do this command. This is my binary, and I do the stats. And if you open this, you will see 10 calls to kernels. One is line. Okay. and a lot of information about GPU ID, which GPU runs, which queue you are, process, LDS if you use, websites and dispatch, and especially the time, okay? The duration in another is the last one, so you see the duration, right? So if you see something, huge variation in duration for same, of course, problem size, same kernel, it's an indication of something strong. By ROC, I mean something you have to identify. And if you open now the statistics file, now what you see here is like 10 calls, okay? 10 calls, total, oh, yeah. So, okay, 10 calls, total duration, average, and percentage. Because 100% of the time is this, of the application is this kernel. I don't see any question for the moment. Now, if I go and do, I have lost the, let me take the reservation now. I know, yeah, maybe 20 minutes. It's 29. Come on, 30. Let's see. I hope now. Okay. Yes. Now I add the heap trace. Okay. Before I had stats, it's only time. I add the heap trace. Oops. Yeah. Something with the wrong trace. Oh, yeah. Losing a log. Then you see start here that heap trace activated. Okay. And now what you see here, new files, heap stats. Okay. And if you open the heap stats, you start seeing which heap commands are called, okay, another layer, some other things. So 20 calls heap memory copy, total duration, average, percentage. That's interesting. Most of the time is heap memory copy for the heap stuff. Okay, so the last kernel takes minimal time, heap malloc, heap free. And of course, this is a small example, right? We have seen codes with a really big list, etc. And if I go to add the HSA trace, now some people will say, why? Okay, more things I add, but this is a small application, right? In a real application, more things I add, more the overhead, right? However, sometimes HSA is interesting, and I mean there is I'm not sure documentation, but more like a PDF with the HSA API to not to read really. You don't need to be expert on this, but when you visualize, if you see something HSA calls to be like long time, something strange, maybe you like to investigate. And now, for example, if I open this file, I start seeing a lot of stuff, which, of course, you cannot know always what is everything, right? Because basically, let's say does everything. I mean, takes queues, prepare queues, dispatch, and all of these things, right? So you see here that you have some waiting that happens a lot, for example. The queue create takes some time. So you have to think that this is more random, that when you create a lot of streams, right? They just say handle situations that can take time also, so can create other type of overhead. And so now you saw something else, right? There is this file. It's not only now, it's some time now. No point to open it really. Okay, so this one, and let me see. I would like to copy it if I remember exactly. And you can copy it also to your, your file, Basically, I have already the, which one is it? So I try to, I lost the keys. Oh, no, sorry. This will cause some problems. I try to, it doesn't increase the fonts to the other terminal. I don't know really why. Let me see. For example, I have it already in my config file. So I download the file. Now, because I'm here in WSL, as maybe you know, and I think I have a file already. What about it? Because I'm trying to go to browser. Yeah, 1 moment. I'll try to go to the browser and try to load it and set it. So if you want, download also the file if you have it, so you can play. Now we'll take a warning that it prefers to have a prot of traces that has the other tools and not JSON. I close this. I did the open trace file and okay. So here I start to expand to see what's happening. Okay, and I see here a heap memory copy takes a long time. The first one. Okay, when I click, I see a lot of stuff that better. And here you see the kernels. And when I click, you see from how they're going to initiate it. And I click the W and I start zoom. But I want to go here because I saw before when I was testing. So let me, and you go a lot, as you see. I don't know how efficient it is through the, see the dispatch, okay? The expected dispatch. I click the S to go zoom out. And I click there because I saw a lot of these things. And which I'm not sure why there are so many here. And I'm saying I'm not sure because this is not, when you have here 10 calls of the kernel and you see something first time that you don't see the rest, it means it can be initialization phase, but it can mean also something else. However, here we see that all the wait signals, etc., are similar duration because the duration is basically the x-axis. And you can see the memory copy. And you can click and see everything like that. And you see now, of course, we haven't discussed, and it's not so easy to discuss about all of this, what internally happens. But let's just say you can see what happens internally, and here you can see this. Yeah, I'm not also aware of all of this, what it is. But here's how to kind of visualize your trace. Now, the question is, what if I have a big trace? I don't have any example, in the training. There are some tricks for traces up to 2 GB maximum. Then the Perfetto that you see here, they have a desktop application for, I think it's only for Linux. It doesn't help so much. I mean, it gives you the feeling, but doesn't go much more. Now, the thing that the Perfetto, sorry, this is JSON file, so this is different. The Perfetto that I will discuss later, you can split it with simple techniques, like take 500,000 lines and make it a new file, for example, and split it and try to visualize separate files, etc. Anyway, I don't know if you download it to visualize. I need to go back to the previous. Okay, I'm taking the ROCmD now. So let me share the terminal again. So and now saying that about the Rocprof counters, right? Again, from ROCmD, I'm taking the instructions. Take here and do the hardware counters. If you remember yesterday in the OmniPerf and roofline, some of the counters was like that what OmniPerf does for you without requiring you to do all of these things. So what I'm doing here, I use these Rocprof counters to do the run. So and activate the timestamp. So it's not something crazy or big or something like that. And here you see the counters, and you see here the first counters, second counters, third counters. So I did 3 executions basically. Okay, and if you load this file, it's really, I would say, heavy file because it's too many lines. And basically here it's better to use something like an awk or something. So here you see you need to find, for example, which columns you like that, okay? And you understand, I hadn't activated the base name, so you can see here how it is. And if you go and you check, from the end of from the end is here, I think. You go backwards and you can start seeing how much is the metric. So here, usually, you need like an Excel to export or to import an Excel or awk or something like that. But here is how you take the counters on the Rocprof. So I call them OmniTools. I'm not sure if it's not official, but it's OmniTrace and OmniPerf. And I thank some people here, developers, and we did make discussion about tools when we have some problems or something. This slide you saw it already, but Rocprof we discussed already. Now, why OmniTrace? Why OmniPerf? Okay, in OmniTrace, first of all, it does a CPU plus CPU profiling, heap HSH, CPU, OpenAP, MPI, Cocos, multi-CPU, and visualization through Perfetto. Okay. Now, through Perfetto, you can see which area of the code or not performs bad, etc., which kernels, etc. OmniPerf will go inside the kernel. OmniPerf doesn't, doesn't do CPU or something else. That's only kernels. So that's why there's a nice workflow from OmniTrace. You see the generic view, you see what is maybe is wrong, and you go to OmniPerf to go deep inside the kernels. And you saw yesterday the roofline analysis and some other stuff that are there. You saw that yesterday also. The change I have done here is that OmniTools people said we use hardware counters also, so we have also this arrow here. As I said before, yes, how well I'm using the GPU with the roofline. You can see, for example, if my kernel is efficient, right? And why I'm seeing this performance in hardware counters and timeline trace to see how it performs across the time, okay? And we have these two tools. So about OmniTools, it is an AMD research tool. It is not part of the ROCm stack like OmniPerf. It's a comprehensive profiling and tracing tool for power applications written in C++, Fortran, HIP, OpenCL, Python, which execute on the CPU or CPU plus GPU. Data collection, plenty of dynamically statistical process level, critical trace generation, and data analysis, high level comprehensive traces, critical trace analysis, and supports HIP, HSA, pthreads, MPI, Cocos, OpenMP, GPU metrics, GPU hardware counters, HIP, HSA API, HIP kernel tracing, HSA operation tracing, memory, power, temperature utilization, and CPU metrics are the classic ones, although we don't actually use them in this presentation. Installation, if required. Why have this? This is like how to install it. So you visit OmniTools release pages, okay? Select the version that matches your operating system, okay? So for example, for us, we use the // version, okay? It's like the SUSE, like Linux. Open source operating system. And I download, for example, this script, OmniTools, this is a previous version, open source, ROCm 503, PAPI, OpenMP, Python. And any user can install it in his project, but it's not be required, right? I mean, it's not part of the ROCm, but usually someone from the support will install it for you. There are RPM and the files for installation also. And there's full documentation here. And here I show you, you get a file, you make the directory that you want to install it. Of course, I did this, for example, usually I do it for my personal folder. I make this script executable, and I call this prefix exclude subdir, and then I export the path to include this. Basically, sorry, here is the bin, and source, and that's it. The tool works. It's really easy. Now, it has the runtime summitation, which is dynamic binary summitation. You can summit a lot of data and increase overheads. Sampling is summitation, OmniTools sample, that does sampling. Attaching the process with -p or binary rewriting. It will not submit the dynamically linked libraries, thus lower overhead and faster execution time. And this approach is recommended for the target executable uses process level parallelism like MPI. And to submit dynamic libraries, I don't include in the slides. There is instruction how to do binary rewriting with libraries. Now, for problems, create an issue here, okay, GitHub issues. And I said the documentation is here. How the execution happens? You do this run with the options that you want, OmniTools option, -- and then this application. So this -- separate the OmniTools options from the application. For sampling, use OmniTools sample, okay, OmniTools options, and again the same. Now, in binary writing is a bit different. You do OmniTools options, -o, what's the name of the new executable, basically not library or executable, and then this is your binary. And you run the name, the new executable, okay? So basically, it creates a new executable that's instrumented, and you just run it after. And we'll see that. Now, OmniTools has a big, not a big, it depends on the configuration file. So in the configuration file, you can define many options, what you want to do with execution. So when you execute this command, you see this table with the environment variables, their values, and the categories. And I will go fast to the second one because here you add the options, this brief description, and you have description of the variables, right? What it is. Okay, so that's really, really nice when you see it for first time. I'll give you an example, right? OmniTrace use ROCtracer. If you don't use ROCtracer, you cannot really trace the kernels. Okay, so it is important if you have kernels, for example. So that way, here I give you slides like a hands-on that will follow after the presentation. You do this command and you create a omnitrace.cfg file with a default configuration. If you do this command, that's all, and I give a different name. For each declaration has description, so you can read the description inside there, which is quite nice. To mention something, when you do a run, because you can also not run, right? Because this command doesn't need GPU. If the file already exists, it will ask you to verify to override, and you will never see it with this run. So you can do that. That's forced to override something, a configuration that already exists. Then when you create it, you have to define omnitrace config file equal your path and this file, whatever name file you give. Okay. So if you don't define this, it doesn't consider that it has a configuration file, and it will do something minimal. Now, again, I give you the instructions. I will do it later. Get and compile the example. The matrix transpose is included in the heap. And when you compile it, you execute it. I put time here to take the time, okay? srun, that's a simple matrix transpose, just like that. And this is 1.2 seconds, right? And when I do dynamic instrumentation, which I do like that, omnitrace, and you remember dot matrix transpose, then starts running a lot of things. I have removed them, and it takes 1 minute 27 seconds. The 1 second became here 87. So that's a lot of overhead. I don't mean that the tool is bad. I don't mean like that. I mean that we have to be careful what we're doing here. And let's see what functions are called, etc. So if we do nm demangle the matrix transpose and grab the TNU to see which functions are actually we call it and we use, and they will be instrumented. So we see a lot the STD, right? The STD ones is not something that we control, and we can say, okay, it's easy to remove or whatever. And you can see a lot of routines, functions that will be instrumented. So we can do something about it. Because with the binary mode instrumentation, only the functions under text are instrumented. So if you do binary writing, it's only the ones under T that is instrumented. Now, if we see which functions are available to instrument, what we do is, this is for verbose mode, but with the simulate means don't run the binary, simulate to see what I want to do, and I want to print the available functions. Print available functions, and I will see here which functions are available in the binary that I'm using. And you can see here is quite plenty. And also the matrix transpose and the CVP, you see here the main, you see here the CPU reference in the code, and other stuff. So if you want to include functions, so if something is not included because omnitrace, I will say later, takes minimum specific number of instructions per function to instrument, you can say does I function name 1, function name 2 to include them for sure in the instrumentation. If you want to exclude because it's not excluded automatically, is does E function name 1, function name 2, etc. Yes, and as I said, the simulate flag will demonstrate the available functions, but it will not run the matrix transpose executable. And let's do the binary rewriting, okay? So basically, omnitrace again, print available functions is not necessary. I do it more for me to see. Does O and the new binary, I call it matrix.inst, does matrix transpose. So here you can see that main found, I don't usually use the API. This is not an API application. And I found some OmniTrace. There's some OmniTrace calls. Now, the fault implementation is the main function always, and function of 1024 instructions and more for CPU. Okay. You submit routines with, for example, 50 instructions, add the options, does lowercase I 50 to submit function of 50 instructions and above. Of course, you don't want to do that if you're not sure what you're doing, because you cannot add overhead, etc. This is an example that this functionality exists, but be careful when you do it. And then I have the binary write, and I said, okay, now I just execute this. I don't need to include OmniTrace because it's a binary writing. And now you see here, it takes 0.8 seconds. Okay, even a bit less than the initial one, but okay, this can be variation, etc. And what you see here in the output, you see here the path that I ran, for example, and you see here Perfetto file. And if you remember, the Perfetto is a visualization tool that we used before, and it's Proto, not JSON. The Proto is more adaptive. And here you see ROCtracer.txt whole clock. And why I have these files like that? Because if I open the ROCtracer, as you see, let me go a bit back, sorry. The output is OmniTrace, your binary, matrix.txt is my binary here, right? Output, a timestamp, of course, timestamp is always different, and the file. So this is kind of the type of the output structure you will take. So if I open here, this file, the ROCtracer, I will see, okay, I see HSA calls, etc. And of course, it's also here's the kernel, okay? So you can see all this information, right? Count, depth, metric, percentage of itself, and stuff like that. So you can see this information. And when I take the Perfetto file, I copy to my laptop, and I go to visualize. Look what I see here. Here you see CPU stuff, and here it's GPU, okay? GPU memory utilization, GPU power across the time, GPU temperature. So you start seeing the metrics across the timeline in Perfetto. And this is the beginning of the application. So yes, these things now for the GPU, this comes from the ROCm SMI. And if you don't know what's ROCm SMI, it's like the NVIDIA SMI, right? That you see the current temperature of the GPU, the utilization, etc. So these are coming from there, and they tell us how the peak memory increases, etc. And this comes, of course, it's statistics, right? It's running every, I don't know, every few microseconds. I don't know, I'm not sure. And if I move, okay, I move somewhere. I see here the kernel. Here I move more right, the timeline, and I see the copy hosted device, and start seeing various things. Now to mention something, it's not perfect. Sometimes the Perfetto does some strange calculations we have seen. So always you have to see exactly what's happening. Now, let's see the hardware counters. What you see here, if we execute this command, OmniTrace avail, this is to remind you a bit the puppy avail, but that's all. You will see all the counters, okay, and description, okay. Now, you see here it says device equals 0. If I use, I don't know, SLU inst device 0, I will instrument the counters only for device 0. So I think with comma, you can say 0, 1. If I remove this, if I remove it says only this, then for all the participating GPUs, I want to utilize the counters. So this is the trick how to select specific or all the GPUs. And I mentioned this again. Yes, the VLU utilization, the percentage of LUs active in a wave. and low is likely due to high divergence or a poorly sized grid. So there are some nice counters that can give you, hints. Something's good, something's bad, as I said also previously. Now, and also we'll do that later. Declaring your configuration file. Okay, the metrics you want to profile. So in the configuration file, you saw that there's a lot of metrics. So I should declare OmniTools ROCm events, and I declare these ones. It's for all the GPUs. If I do device 0, device 0, device 0, it's only for device 0, okay? In my case, I use also only one device, but doesn't make difference, right? So this is a way that you go to your CFG file that you created to define which metrics you want to utilize. Okay. And I do that, and I run like that, nothing changes, only my CFG file is changed. And what I see here now, new files, TXT files, were from the counters that I use, okay? And of course, the perfecto file will be increasing the size also, right? And you see here now, here you see also sampling GPU memory usage is here. Now, sometimes reading the TXT files doesn't help because the values seem strange compared to the timeline. And here we are, and check here. How you know that this is counters from the GPU, and I mean the GPU busy, right? And not from the ROCm SMI. Now, GPU, you see here GPU busy is at the end. When it's GPU busy, this is ROCm SMI. When it's device GPU busy, is something that I have declared, and this is a device. Okay, this is from the device directly, so it's a good, let's say, metric. And you can see here, I think the GPU busy from the ROCm SMI is 0, while here there's something working because also have the kernel. That's why I say sometimes the matching in the timeline is a bit, let's say, strange, I would say. But anyway, this is how you know that this is a counter that you have declared to ROCm events compared to the ROCm SMI. Now, something else that I really like, before you saw the visualization from Rocprof and how it goes. Now, if I use in my CFG file, OmniTools use sampling false, which I think is the default, you can see here the different colors is routines and calls. But if I use here, please use sampling and do 100 samples per second through sampling frequency. This is on the CPU side. And you see here how deep it goes and how deep it will go here. I think, yes, I will zoom also later. More information about the call stack. Take a lot of information. If you go and zoom, you start seeing the full call stack, what happens. Okay, so this is quite nice to have information when you are not sure what's happening. It's something that I really like from this tool. How to see kernel time? If you open a binary here, it's your binary, right? Your timestamp, whole clock. You will see the kernels, and you see variation, mean, maximum variation, etc. And here's a metric, right? Whole clock. However, you see this is the depth. So it goes like it's not flat profile because depth. So it calls, for example, this kernel calls heap memory copy, etc. But you want to know the exclusive time of the kernel of the whole, not to go to different parts of this table and try to sum up to find the timings. What's the trick here is that you use the time memory in order to have all the information for specific counters during the timeline, and you say, I want my profile to be flat, okay? Flat. So when you define this in your CFG, then there's no, then everything's flat, and all the timings are specific per kernel, for example. So this is a way to take the timing per kernels. As you can see, there's a lot of information, right? A lot of, sorry to go back, in the CFG file, there's a lot of metrics, not metrics, but variables you can change. So this takes some learning curve a bit. User API, I want to start to stop the trace, right? Specific moment, how to do it, for example. Or enable tracing it on a specific thread, and not to apply to subsequently created threads. And so you use a start trace, use a stop trace, use a start thread trace, use a stop thread trace. And all the API calls are here. This is just an example, right? Because at the end of the day, in order to avoid overhead, it's quite crucial to try to say, I want to profile only here or there in order to not have a lot of overhead. API. So in order to here, I have an API application, okay? Basically, I use this from OmniTools, okay? And I call it API, basically. And I do binary rewriting, okay? So the API becomes API.inst, and I run this. And then I have one file per API process, okay? So this is quite good, and you can compare, etc. It's quite great. Now, visualizing one perfecto per API process. So this is API 0, API 1. You see here the differences in all of the things. You can see it's the API calls. So you can visualize its trace alone, okay? But as I said before, you can play easily to merge. And what I do here, I take the 0 process proto file, the 1, and I just merge them. I mean, I do cut all process proto, and then I open both of them. And of course, you can see there's some empty, I mean, because of some accounts, etc., not really initialized, but not information basically. And you can see up and down exactly how it is between the API process. Obviously, for large number of processes, a different approach is required. If you're willing to visualize many processes, right? This is 2, and it already doesn't seem so perfect. Imagine to have like a few thousand. It's not this is the approach. OpenMP. So I used an example from OmniTools again. Build the code. We use a OpenMP LU binary execution, and I do like that. I create a new instrumented binary, okay, in the simple case, and I run the binary, the instrumented binary, okay, and then you have 4 threads, okay, and you can see here the from 0, 1, 2, 3, and the formation. So the tool also, as we said before, does also the OpenMP instrumentation. Now, the OpenMP visualization, I was not surprised, is a bit like that. Okay, so I cannot see so good, but here you have the information about the functions, and you have the 4 threads and the information here to visualize. Python, yes, that's also Python, and I wanted just to demonstrate one example. The OmniTools is installed in where is the OmniTools installed? Here is a Python. We set up the environment, okay, with Python path, and I use the Fibonacci example from OmniTools examples, and I run it with OmniTools Python like that. There will be a new directory called OmniTools binary source output contents, and the path documentation is here. And if I do OmniTools source output timestamp and wall clock, you will start seeing, because this was a Fibonacci, and start seeing the labels, what the routines is calling, the count, depth, etc. So this also works with Python. And here's the Python. See, here's the Fibonacci, visualizing the perfecto trace. You see here the counter. The sampling seems to be active because we have a lot of information. So you can get a really nice information about, you can see here iterations, right? And if the iterations are keeping to be uniform, it's a good sign. You can take a lot of information. So just to zoom and see what you're looking and to be sure what you're doing. OmniTrace sample, for easy users of OmniTrace, there is also OmniTrace sample. So if you forget all of whatever I said and you do OmniTrace sample, you will have less overhead. Not for everything, but easier. Not of all the declaration of the configuration file apply. So this is something that maybe will change. For example, in order to use the counters, I have to run the command like that. OmniTrace sample. This is like a trace profile, host devices stuff. The counters are declared them like here. That's in the binary. So this is how it works with the OmniTrace sample. And you can do OmniTrace sample. That's it for more information because there's a lot of information about what to do, etc. Tips and tricks. So because I was instrumenting a big code and I had issues and discussion with developers, etc., I started gathering some information. And I say, my preferred timeline seems weird. How can I check the clock skew? If you do in the configuration file OmniTrace verbose equal to 1 or higher, it will print the timestamp skew. OmniTrace took a long time in the finalization. How to check which part takes a lot of time? Again, OmniTrace verbose equal to 1 or higher. So at the end, you'll see the run finalizing and maybe staying there a long time and you say, okay, what's happening? So that's why you want to know information, especially to report. It takes too long to map ROCm SMI samples of the kernels. Use temporarily disable ROCm SMI. This is a typo, it's off. Okay. I had a case that a code was calling 6.7 million kernels totally. I couldn't finish it, and finally we did this trick and it finished. If you're doing binary writing and you do not get information about kernels, declare this in the environment, not in the CFD, in the environment, and be sure that the OmniTrace use ROCtrace on in the CFD file. My heap application hacks in different points what to do. Try to set HSA enable interrupt equal to 0 in the environment. This handles different how heap is notified that GPU kernels completed. So I had again this case that I could fail in 3% execution up to 93%. And I was wondering what happened, and the developer helped me to say, okay, try this and this worked. It is preferred to use binary writing for MPI applications in order to write one file per MPI process and not aggregate it. So to write one file per MPI process also use this. OmniTrace use PID. So they will use the process ID in the file name. So you have different files. My perfecto trace is too big. Can I decrease it? Yes, with version 173 of the latest, declare OmniTrace perfecto annotations to false in your CFC, and this will decrease the size of the file. Full documentation is here. Check it, it's quite good. And it's quite, yeah, it has a lot of information, but we still improve it. So I was thinking because we load the module Okay, we have installed it in yeah. So what happened? We found out that there was a problem with small developer. Sorry. The version we use a bit older version for the 5.2. I think. Yeah. Okay. So it's not the best approach like that, but I don't know, they don't have module. So yeah, they have. Okay. So with 5.3, I think the OmniPerf was failing, while it doesn't fail with 5.3 in another system. So it's something strange here. Oh yeah, what? So do the unload. Yeah, first unload the ROCm 5.3, load the 5.2.3, and that should be okay. Also reserve again like that. And I will say here that something, no, that's it, not. The command here is two commands in one line. This is the, wow. Okay, this is 5.3. Where is that? What happened? It uses still the 5.3. I'm not. Yeah, why? Okay. So we like that, huh? Okay, I need to speak. So I do this command and I can see this is. Let's click it again. Okay. I see environment variable, the name, the value, and the categories I said before. And if you take the other command to description, you can see better. Ouch. Okay, I have two big fonts, but I cannot do a lot of things. And also, it can support also caucus, right, etc. So you can see information about variable and what's the description. Now, I create like that. If I don't have it, I don't have it, okay? So I create a configuration file. And if I open it, you can see now configuration file for OmniTrace, this one. Enable Perfecto backend, this one. So you can see information for each of them, okay? So to not to get, now here, for example, process sampling, right? Information. So it's really good to guide you step by step. Okay. And now here I need to define it, that this is the file. Oops. So once I had a typo here, which I was writing by hand in the OmniTools config file, and I had crazy results I couldn't understand because it was not using actually configuration file. So be careful. And I'll copy this example. Compiling. As here I am on MI250, the architecture I expect to be. No, I need it finally. So this error is classic that you need to define. So I need to correct the instructions. And if I run, okay, almost 2 seconds, etc. Now, if I do dynamic implementation, okay, OmniTrace does, and the binary is quite simple, right? Oh, the copy paste something. No. See, yeah. I stood here, no? Correct. So this is wrong in the instruction, sorry. Now here, the dynamic instrumentation, it is again Dynist API. So this will instrument a lot of things. It will tell you also what happens. You see here finalizing, so it takes some time to finalize. The backtrace. There's also here, it tells you what functions are available, excluded, overlapping, or instrumented. Wow, now it takes more time than what expected. Oh. Oh, something failed. What? Sorry, something failed here. Why? That's not good. In order to kind of fix it, it was to change this machine. I'm on Lumi now. So on Lumi, this command just works. So it's something, I don't know what was the ROCm or something, we'll have to check. Because the error was coming from RocTracer. Yeah. So basically when I do dynamic instrumentation, the time, as I said before, is 1,024 seconds. That's a lot of time. Because before it was like close to 2 seconds. And we'll do this demangle to see what functions are called, etc. And as I said, with the binary writing, we'll use only the text ones. And if I do this command to see the available functions and simulate, so it doesn't really run it. Oh, it takes time. Yeah, I'm afraid the file system is not so responsive. Yeah. So this will print the available functions that can be instrumented. And That's not normal. That's I think the file system on Lumi is slow at this moment.
Good to hear that it works on Lumi.
So here you see a crazy number of from other libraries and other stuff. What happens? So in order to avoid all of this, we say, what if we write the binary, the available functions, and check the difference? Of course, you lose information, right? But you don't need all this information. That's why I said you can include, exclude functions that you know that you need. And I think now it created the binary. And if we run the new one, so that, oh, okay, yeah. Oops, sorry. I need to add some paths because this is a bit custom installation. .5 seconds, okay? From 1 minute, 27 seconds. 0.5, of course, less information, right? It's not the same, but so you see my outputs like that. And I see, okay, the heap calls that they were captured. Now, this is the activity, right? The ROCtrace activity. If you want to see, yeah, you see some time, right? You see here the variation also of the mem copy. You see some other stuff. Now it's 2:57. I want to show just that. You see here the file that I have this file. This file is a visualization file. Let's go to we take to Perfetto and you visualize it. I will skip the visualization now because it takes more time. And to see the hardware counters that I showed you before in the so you see here the list of the hardware counters is a lot. There is no description, just to mention that a colleague, this is the GPU stuff, okay? That the colleague works in documenting the GPU. Here's a classic puppy. The colleague works in documenting the documentation for the CPU counters. And if I go to my okay, so I go here and define it like that. You saw there's a small increase, but it's vocabulary variation. But also you can see here now the files that were created, right? And now if you visualize this, you will see the device, GPU busy, etc. Now, I will stop for the next talk. I will try to check, because I'm here on Lumi, I will try to check what happened to the cloud, because I have copy commands from there. So I expect that it is working, but I need to check what's happening in order so you can follow these instructions also yourself.
All right. So hi everyone. Today we'll be talking about another tool which is provided with the ROCm stack. It's an essential. I think it's one of the essential developer tools. It's the debugger, and and we'll see how we can use this debugger to help our efforts in porting the application, and especially when we want to understand how the application is behaving. And especially when we start running into some issues and want to try and debug that. So ROCgdb, or the AMD ROCm debugger, is a source level debugger for Linux, and it is based on the GNU debugger, the GDB. So it tracks the upstream GDB and all the standard commands that, if you're already aware of how we use GDB, they also apply here. And what is good is that you can do both CPU and GPU debugging using this tool. It is considered as a prototype because like most of the changes here keep like track of the upstream, and it keeps focusing on the source line debugging, but there is no symbolic variable debugging yet, which is available in ROCgdb. So it can do a lot of things, and to showcase, what are the features and how to use ROCgdb, I thought it's easier if we go through, if I drive this entire talk using a simple example. So I'm using a SAXP kernel, which basically is just like if you have a vector, you want to multiply each element of a vector by a scalar and then add it to another element. And you can see that on line 10, like between line 6 and line 10. That's my main SAXP kernel. So here, what I'm using is I'm using an array of size 256, and it has two groups. Each group has 128 work items, and those work items are also divided into like two like each work group has two set of waves of 64 length each, and we'll see why this is important when we go forward. But essentially, this is a very simple implementation of a SAXP kernel, as you see here. So, like say for example, I'm going to intentionally break the code by commenting out lines 20 and 21. Let me see if I can actually use a pointer. Yeah. So at line 2021, I'm going to like intentionally comment those lines out. And when I comment these lines out and when I try running, one of the things to know, important things to note is that if I don't place a HIP device synchronize at the very end, the CPU thread may quit and may exit, like executing your program before the GPU even gets to report this error. So it's important that we keep the synchronization in here at the very end. So anyways, so I'm going to put these two, I'm going to comment these two lines out, and then when and then I'm going to try and build it. So building is pretty easy. I'm sure you've had a couple of trainings before this and a couple of talks. So you can use HipCC. To HipCC, you can provide a flag, which is offload arch, and you can provide an architecture if needed. If you know that you want to compile it for, say, for example, MI50s or MI100s, you can provide the architecture GFX 906 or 908 there. And then you can compile your code. Now, after the code is compiled, and I've created an object file, which is called SAXP again, and I try running it, you'll see that it gives me a page fault error, that I'm getting a memory access page fault, right? But I want to know now, why is this happening? And this is essentially where the debugger comes into the place. So at the very first go, I see this error, and I pick up ROCgdb, and I execute inside the GDB mode. So I just say ROCgdb, and then the name of your application. When you run that, it's going to say, sorry, when you go inside GDB and you say the run command, it's going to start executing your code inside GDB. And it will say that, hey, thread 3 found the segmentation fault, and that segmentation fault is somewhere in your kernel, right? Now, it is reporting that it is in SAXP, but I want to know exactly what's happening and where it is. And to do that, to get more information, when we compile, we have to add this GGDB flag to your HipCC compiler. So now when you do that, and then when you redo, sorry, I think I went, yeah. And when you redo more of it, you get more details like what kernel, what file, what line. So it will tell you that, hey, it happened in SAXP source file at line number 10. And then this is where things are happening. And then that's helpful in understanding what's happening. And then for people who are more interested in learning about, memory violation and things like that, you can see that if you compile and if you run it with the AMD GPU precise memory mode, as written here, it will report like more details for those interested. But I'm going to stay away from it right now because we don't have a lot of time to dive into all those details. But yeah, we can definitely answer those questions later. So now I'm interested to see that what's happening. Like, okay, my fault is happening inside the kernel, but I want to see the CPU trace or the stack, right? So, what I'm trying to do here is that inside GDB, then I just say info threads or ITH, and then it prints out or it lists the different threads or different waves that are available. So the sec fault, like I said, was inside the GPU, and my CPU is but it is not showing my CPU stack. So that's why you list the threads, and then you can see what are the active threads. Like, so for example, the thread that reported was actually a GPU wave, which is depicted by a star here in front of the wave ID or the thread ID. And on GPUs, each wave is treated as a thread, essentially. And I'll talk more in detail about why we have 4 threads and 4 waves and all of that a little later. So now I want to see that, okay, going back, like the CPU threads here I can see are 1 and 2, and the rest of them are denoted by AMD GPU wave, meaning that they reside on my GPU. So I can switch the context and I can say that I want to particularly see what's happening inside my CPU, and I can say thread 1 or T1. So that's the short keystroke that you can use. So when I do T1, it takes me inside, it switches to thread 1, and then it will start showing me more details about that. So you can see that it was inside the HSA runtime. But more importantly, how did it get there, right? Like, how did it get to the libhsa runtime? So then I can use the command where. And when you do where, that's when it's going to dump out all this information. It's going to show you the entire CPU stack. And you can see that at the top, eventually when the code is executing, like from the main, it ends up going to hip device synchronize, and that's when it calls the hip runtime API, which then calls my HSA queue. So this like collecting a backtrace or a CPU stack trace is really important in trying to understanding what was the path that of execution and where all your threads jumped before it finally encountered some errors. So a quick tip on Frontier and Lumi, CPUs have 64 cores, and each core have 2 hardware threads on it, so giving you 128 threads. So if you're debugging an app with OpenMP, and if you don't have OpenMP num threads environment set, you will see 128 threads in ROCgdb. So it might be important if you're just debugging a small app and you just don't want a large overload of information being dumped on the screen. Just say OMP num threads equal to 1, and probably that will be much more helpful, especially for GPU codes. So a few important things now. I showed you in a nutshell what all ROCgdb can do, but now let's take a step back and let's start investigating small features, or like each and every feature that I think is important. So the first is adding a breakpoint. Now, let's say, for example, I want to investigate a certain section of the code, and then and when that portion of the code has been executed, I want to put a breakpoint so that the execution should stop. So you can do that just by saying B or breakpoint, and then you can provide the name of the file and what line number. So for example, I'm saying I want to put it at line number 22. But then if you can see here, it says that breakpoint 1 was added to the file, but at line 24. So I told it to put the breakpoint in 22, but it declared it as line 24. And why is that? So just to make sure that we remember what our SAXP kernel looks like. So this is the kernel, and this is the entire implementation. And line 22 is essentially like it has nothing. It's basically a blank line. So essentially what happens is that when you compile with HipCC, your default optimization mode is O3. So if you want better correlation with your source code, and I'm not saying it's always necessary. Sometimes, ROCgdb can take any level of optimization, O3, O1, O2. But if you really want like good level of correlation, and especially with your ISA or like the assembly instructions, and you want to do a bit of correlation there, then sometimes I've seen that the bare minimum, the O0 is much better. So anyways, when we compile with O0 and then we try running it again, now you will see that when I put the breakpoint on line 22, it reports that, yeah, the breakpoint was indeed placed there. So now again, with a short keystroke, R, instead of just typing all the commands. So in ROCgdb or like in GDB, you can use the shorter version keystrokes for the entire command. So info threads becomes ITH. And for run, you can just say run. For step, you can just say S, and we'll see all of that later on. Now, if you are in a particular thread, like say, for example, on the second, like in the middle of the screen, I'm showing that when I say info thread, it is showing me 2 threads, and there is an asterisk mark right in front of thread number 1. Now, I want to see like, where are all these threads, like on which device it is. So in GDB, I can just say show architecture, and then that gives me the information of what devices are present and where are these all threads spawned. So when I do show architecture, it will say that target architecture is set to auto. Now, you can put a breakpoint at the kernel again, like at the kernel itself. So instead of saying breakpoint, let me go back, sorry. Instead of saying breakpoint at a particular line, I can define. So if you have a kernel or a function or like some class, you can just say, put a breakpoint, and you can provide the name of that kernel. So the function SAXP, like at that point, is not defined. So it's going to tell you that, hey, can I put a breakpoint pending on a future shared library? And you can just say yes or no if you want, and you can go forward with that. And then once you set that, you can say continue. You can hit the or again. It's a shorter keystroke C, and then it will start continuing, and it will go till it hits that particular breakpoint. And once we hit the kernel, if you do show architecture again, it's going to say the target architecture is again set to auto. So, but here you can see that it also gives you more information compared to others. Like last time, the threads were on the CPU, so that is why you were seeing the XADA 86. But now it's going to say that, hey, this particular thread, or like now this particular breakpoint, when you hit this thread, is now on the AMD GPU and GFX 908 device. A lot of times, I mean, in these last few slides, you might have realized that I'm showing you the commands, but sometimes it's easier to have, your source code displayed in tandem with your console. So there are a lot of graphical user interfaces that people like to use. You can use the 2E mode in ROCgdb or like that. In ROCgdb, or you can use different courses based implementations. So because essentially ROCgdb is GDB, any front-end GDB can be used here. So you can use CGDB, you can use ROCgdb, and things like that. So here we have a tool that I'm going to be showcasing a little, which is ROCgdb plus GDB GUI, and you can use it's a web-based GUI. And at the end of the presentation, I'll just post a slide where I can show you how, along with if you have a web browser like a Chrome, how you can install all of this, and how you can do remote debugging. Like especially if you're running it on like a cluster, and then you want to do um, debugging on your like on your local screen. So anyways, so I'm using GDB GUI, and then I do the same thing. I put a breakpoint on line number 22. Now, to take a few steps back and to go towards the hardware side, I'm guessing you already had like some training on how the GFX 90 architecture is looking like, but let's take a compute unit out of it. So each compute unit has a scheduler, and then apart from scheduler, it has a it has four 16-way SIMD units with 64 kilobytes of registers. It has an LDS about 64 kilobytes. It has a scalar unit, a scalar register, and then an L1 cache. Now, to think from a point of view of ROCgdb, each of those SIMD units can become a core. So essentially, you can think that you have a 64 so that entire SIMD is basically a core with it's a code with a vector length of 64 lanes, and it can execute up to 10 threads, and it containing about 256 vector registers inside of it. So this is what you can think of the hardware from a ROCgdb standpoint of view. So now, when we list all the threads, you can see that again, at the top, it is showing threads like 1 to 4, which are all on the CPU. And then it is also showing you some GPU waves or threads. So like I said earlier, all the waves that ROCgdb is showing, it is treating each wave as a thread. And currently, we are on thread or wave number 5 on the device. Now, this is actually giving you a lot of information about the kernel also, and also about like the wave which is executing that kernel. So it is giving you information about the agent ID, the HSAQ, the dispatch number, like how many times that kernel has been called and things like that, the wave ID, the work group, and all of that. So this is important because like sometimes when your particular wave is misbehaving, or if your hardware is misbehaving, you can correlate to what's happening and like what particular threads are like causing issues. So there are a lot of other things that you can also do with ROCgdb. You can like inspect and modify registers. So I just showed on the hardware side, we have vector registers, we have scalar registers. You can inspect memory aspects of your code. You can inspect and modify like the local data share, like what's happening there, like how are you loading in the LDS, and like how you're storing or writing from it. And you can step through the assembly one instruction at a time as well. So I'm going to showcase some of that right now. So again, to inspect the assembly, we have a lot of tools, and during the exercise, I'll show how you can do all of this. But essentially what it does is that alongside your source code, it gives you a view of your assembly instructions next to each other. So, and it also helps you correlate, like different GUIs have different highlighting features. So sometimes like when you're stepping through each instruction on your source, it also correlates to the assembly level instruction on the side panel. So for example, here we have a lot of check condition for our which is happening. So it is creating an execution mask. It is, and if the execution mask is 0, then it will quit and it will exit out of the loop here. And to execute this kernel, there's a lot of arithmetic addressing which is happening before. And then at the towards the end, you can see on that you can identify the global loads which are happening. And then at the end, you can also identify the FMA operation, or the fuse multiply add, which will end up happening because of the SAXP operation. And then once that is done, you'll see a store, again, a global store where your results are getting dumped. So it's helpful because, again, you can imagine that, you can imagine that by going through, like if you are aware of how your hardware should look like, and you have certain understanding of the assembly level instructions, you can look at things like registers. You can look at things like, how much register spilling is happening, how much branching is happening in the code, and that gives you a set of some sort of an understanding of how your application is behaving on our hardware. So before I move forward, like, are there any questions? Like, feel free to interrupt me if there are any questions. All right. If not, so again, I mentioned before that you can say show architectures, and you can see different architecture where your thread, where your thread is residing at that particular moment. But say, for example, you want to understand, like, if you're working on a system which has multiple devices, and you want to list all of them and the properties of those. So you can say info agents, and that will print out or like give you a list of different devices that are present. So for example, on this particular machine that I was running, we only had one MI200 series GPU. So you see that listed here. It has, again, 110 cores. So when you multiply 110 compute units, so each compute unit is, again, a core here. And then when you multiply that by 4, you get 440. And then you can multiply that by 8 to get the overall SIMD number, which is located here. You can do a similar thing for HSA queues. You can do info queues, and then that will spit out the queues that are available. So say, for example, like for our particular application, when I say, and this one particular device, I said that there was one MI200 device. So when I say info queues, it prints out the 2 queues that are available on that. And then you can see the AQL packets being written so that our kernel is operated upon. And then going a little more detail about the dispatches. The dispatches are important because, like I've already mentioned, it gives you details, obviously, about your agent ID, your HSAQ ID, your dispatch ID, but it also gives this other information about, what was your block or like the grid block dimension size. What are the group dimensions? Like, are you able to saturate all the GPU or not? And what is the kernel function? And like you can see all of that here. And so again, for that, you can just say info dispatches, and it will tell you all the dispatches here. Because there is only one kernel here, and it's being called just once, it's you'll just see just one dispatch listed here overall. But say, for example, if you have a kernel, and if you're using say, for example, if you have an application and you call a kernel particular times, and if you're saying for dispatches, you can expect to have repeated list of those particular kernels there with different dispatch IDs. So like I said, we can also investigate registers. So in my example, I have like different vector registers and scalar registers being used. So most of the operation is like in vector registers, I'm using V0, V1, V2. That's what my application ends up using. And for scalar registers, it spans from S0 to S9. Now, there are some other things like you can also see what's the execution mask and what is the program controller, the programming counter, and things like that. And that helps us in understanding, what are the values which it is taking, when it is, and if, say, for example, your application is not behaving right, you can investigate each and every one of those registers. And register spelling is an important aspect, although I'm not touching that in detail. But you can do that here. Like if you see that there are, if your application is using a lot of registers and then it's spilling all of them, so you know where to go back into the code. You can correlate that with the ISA again, or your assembly instructions again, and then you can go back and you can change and modify those source lines. So that's really helpful. So say, for example, in my particular code, if I want to investigate V0, I see that like there are 4 waves or 4 threads, if you remember from one of the previous slides, which are residing onto the GPU. And basically, V0 has all the information about my X, about my vector X. And I can see that 2 of the threads out of, or 2 of the waves out of 4 have V0, but and they essentially contain values from 0 to 63, but the rest of the 2 waves, say for I think 6 and 7, they have values from 64 to 64 to 127. And this is, again, like I mentioned, is important to understand what's happening inside your code and how you're using your work groups and how you're using and are you able to saturate the GPU well to get more optimized performance out of it. Again, similar thing with scalar. Similar thing with my scalar registers. And essentially what I'm trying to just show with these set of slides is that you can investigate each and every register here. And so to do that, what you have to do is just type the command info register, and you can say what register you're trying to look at, whether it's S8, S9, so you can keep typing that, and it will dump out the information for that particular register. So for scalar registers, you only get obviously like scalar values, but for vectors, it dumps out all the vector related stuff onto your screen. Now there's one more important, another important aspect is like sometimes, especially when you're doing GPU programming and your work, and for example, you're trying to see, what, as your threads are spawning and as you're executing your program, what are the HIP runtime APIs that are being called? You can achieve that like inside GDB just by setting the environment variable AMD log level 3. And then when you run that with GDB, you see that a lot of the HIP API stack is also dumped out while your program is executing. So this actually holds true even outside of GDB. Like when you do AMD log level 3 or log level 7, and when you just run your application, you'll see a similar split there. But it becomes slightly more helpful inside GDB, because then it also starts printing all those information that I was talking about before, along with your HIP API calls at the right places. So you can see different HIP APIs colored in green, for example, the device synchronized, the HIP free, and all of that. So you can and it also gives you the thread ID and all of that. So if you want to just investigate a particular wave, so you can just select that particular wave by saying by just saying thread, the wave number on the GPU, and you can just hit continue or run, and it will just dump out all this information. So there was a lot of information bagged here, and I'm sure a lot of people want to use similar stuff. So ROCgdb, I'm just going to leave this particular set of instruction slides. I'm sure you will have the slides later for your use, so you can follow the instructions and you can start using GDB GUI if you like with Chrome. But otherwise, you can also use like ROCgdb in the 2E mode or anything else that you're more comfortable with. But I think that's all I have overall. There are more resources about ROCgdb. Like if you have a ROCm installed, you can actually find some resources, like some manuals inside the shared doc ROCgdb folder, and you'll see a bunch of PDFs there. So that's pretty handy. Or otherwise, you can obviously go to our documentation and website to get more details. That's what I have. It was a short but a condensed talk on ROCgdb. If you have any questions, let me know. Otherwise, we can do the same thing and we can like do more of a hands-on exercise if you guys are more willing.
Okay. So we'll continue the discussion with OmniTools tool. This is another one. OmniTools executes the code as many times required based on the job submission. With that specific option, the application will be executed many times with the various hardware counter, more than 100. So this can take a long time. So when you submit your binary without any options, it can run plenty of times. There are various options for filtering, kernel, metric, event execute mainly for roofline analysis. And there are many data per metric hardware, and we'll show a few. OmniTools provides tables for every metric. With OmniTools, first we profile, then we analyze, and then we can import to database or visualize with standalone GUI, and I will show you a bit. And OmniTools targets MI100 and MI200, and later future generations AMD GPUs. If I'm right, the roofline is only for MI200 series. For problems, create an issue here on the GitHub, and developers are quite active. You have seen this again, so we've fast. So again, they depend on the ROC profiler for some stuff, okay? The counters and some benchmarking. There is CLI, you go from the terminal to see the tables of the data, and you can take a PDF with some roofline. And you can import to the database, although there is also now standalone. And so there is a database with a GUI to visualize through Grafana with various tables and graphics that I will show you a few. And there is also the standalone. Again, I will show you something about this. OmniTools Futures has a lot. Supports MI100, 200, standalone GUI, Grafana. Dispatch filtering means that show me the dispatch of the kernels from 5 to 100 times execution, kernel filtering, GPU ID filtering, baseline comparison, speed of light that probably you know from other tools, kernel statistic panel, memory chart analysis panel, roofline analysis, supported on MI200 only, command processor, wavefront. So I don't need to read all of them. Not all of them are always useful for each application, right? Depends on the application, but some metrics, even with L1, L2, gas, etc., are quite important. Now, client-side installation, if required. So, again, I believe that this tool is easy to install. You just download the latest version, uncompress, load ROCm. No, ROCm is not required for client installation. It's okay. You need Python and install some dependencies, and then build it at the modules, and add in your path what is installed, the bin file. So it's quite simple, and you can install it local in your space, etc. So OmniTools modes, profiling. Okay, you go says, I want to profile this application. Of course, here I haven't included this run before, right? You need to give a name for this workload. This should be a unique name, usually not to exist. Profile options, proofline options if required. That's like OmniTrace and the binary and its options. When you finish, you say, okay, let's do an analysis. And says OmniPerf analyze what? The workload name is this one that you use to profile. And for which hardware? MI200. It will be automatically recognized and we created MI200 directory, okay? So see the connection of the workload name connections. And then you can say ongoing import, OmniPerf database import and connection options that yesterday showed, but these are not public, they are not for all the users, it's more eternally. So its HPC site can have its own Grafana database and use it. But there is also the standalone. And what I mean standalone? You run OmniPerf analyze, that's P, the workload, and that's GUI. And then you open your browser and you go to specific web page and you see a lot of information visualized that I will show you. Now, OmniPerf profiling. I use the example vcopy.cpp. It's located here, okay? So compile it with HipCC and let's call the binary vcopy. Load OmniPerf module. And now profiling, okay, I run one process, one GPU, OmniPerf profile, how I call the workload, vcopy all, does vcopy and arguments for the binary. And you start seeing a lot of outputs, okay, target here, etc., version. In this case, we call the workload name vcopy all, and after the does everything is about the application we execute. And the application will be executed many times for collecting different metrics. If the application takes significant time to run once, then this could be not the optimal approach. So this one, we'll see it in the exercise. If you run it, it starts running for many, many times. So if they are running for once, takes, I don't know, 5-10 minutes, you have to wait a long time. That's why you have to be careful. At the end of the execution, we have a folder workloads vcopy all, MI200, vcopy because we name it vcopy here. You can see all the options with the command OmniPerf profile help to see all the options here, what else you can add after the profile. And analyze. I can run SRAN OmniPerf analyze what? The vcopy all MI200. And redirect the output to a file. Just to mention something, this reads data and extracts information. It doesn't require SRAN really. So if you don't use SRAN at all, and I mean start from OmniPerf, it's okay. But if it has so many requests on login node, I don't want to stress the login node. That's why I do an SRAN. And this file here, the TXT file anymore, will contain a lot of information like top statistics kernels, okay? This one has only one. System speed of light. So what do you see? You see the many metrics, okay? VLU flops, IOPS, and you see here 0.37%, this is percent, okay, of the peak. So the speed of light, okay? You see a value 89, and you say, yeah, but the peak is this one, and this percent, so it's really small. Active compute units, 58 from 110, 52%, which means, okay, we don't have so many actually. And then you see percentage IPC issue, for example, almost 20%, or VLU active threads per wave, 51%. You start seeing information about the various metrics. Just also here that there is, I don't think it's public, but there is an effort that the documentation about the counters to be improved. So for the users to be easy to understand many of these aspects. Then you can see another table, this is far. So something else to mention. You see here the number 0, for example, right? The system speed of light is number 2. And a lot of indexes, right? 2 point something. The table 7.1, wavefront and large starts, and the index 7 point something. And you can see here, for example, what unit it is, what's the maximum, minimum, and average for Here, for example, we don't use LDS at all, etc. Now, I want to show you something. You can execute perf-analyze to see various options, okay? And I will show you the next slide. But you can use specific IP block with -B. So this one, for a big example, even this command can take a few minutes, okay, to extract everything. You can use the same command as before, but -B 0 to print you only this, the top stat. Or the same command -B 7.1.2, it will always print the top stat plus the wavefront. This is a real screenshot, for example. So 7.1.2, why? I wanted this. So you need to know the code for what you want and use it as option in the -B. Okay, so this way it's really faster to do some extraction of the results if you know that you want specific results. If you don't know, okay, you can do all the analysis. And here I was saying that the OmniPerf Analyze -8 has a lot of options, okay? For example, list the kernels. So I can list the kernels to know which one to extract, or list which metrics, and filter the metrics. As I said now, -B, right? -K, and the ID of the kernel to do analysis for specific kernel. And some other options, of course. So there's plenty of options to play with the tool and to do analysis, let's say, a bit more efficient. Now, as I was saying, for standalone GUI, okay, download the data. When I say data, I mean the workloads we copy all. Download this to your computer, for example, and install OmniPerf without ROCm. So there, you need to install OmniPerf. You need some Python and no ROCm at all. Okay, so some Python dependencies only. And when you do this, analyze P GUI, then it starts activating. You open your browser. You go to this web page. Okay, to 8050 port, and starts a GUI of a lot. This is just one example, right? A lot of GUI. Here's a memory chart analysis that you can see, for example, the wave occupancy, the wave life cycles, active compute units, and some LTS utilization of node, and a lot of transfer the fabric, and etc. So it's a lot of information that you can see in a GUI without even Grafana, without even database. Now, and I continue here, the speed of light. So this you will see it in your web page. So I took screenshots, a few to just show you what's going on. And you see here, active compute units, 52%, for example, and the other is really small. Instruction mix, if you have branches, SLU or a VLU vector, etc., or LDS, to see exactly what happens to your kernel. And also, you can see, yes, instruction mix. So integer 32 here, it's the number of instructions per wave. It's a lot. And the speed of light, right? Cache hit, you have here more than 60%, cache utilization more than 80%, etc. Cache bandwidth, etc. So you can see a lot of information. And if you understand, I went back, this is number 2, number 10. We don't have numbers for all the tables, but we skip some numbering, but there's a lot of data to see. And also you can see the roofline analysis. But the roofline analysis, you can do it also just roofline without anything else to have less data. You miss other data though, but you can say, okay, execute and name my workload case this, and do roof only. That's roof only. And the application. Copy the workload to your computer, run this command, and go to the web page, and you will see later the roofline analysis. And you will see, as you saw the roofline analysis yesterday, no need to repeat again the arithmetic intensity, the gigaflops per second, etc., for the top 10 kernels. So you see different colors is the top 10 kernels. Now, I went to Grafana, we have a Grafana server, and basically, I was thinking if I could do it live, but I need to connect to VPN and etc. And I took screenshots. So here normalization is per wave. I have a big copy example. You can compare with baseline other stuff, other execution, etc. You can see system information, right? Ubuntu, what GPU, etc. And you can see the speed of light. So you can see here the Grafana is a bit different than the standalone GUI. You can see value active threads per wave, for example, is 100% utilized, etc. Kernel statistics. I'm sorry, here it's not clear. You have one kernel, 162 gigaflops, almost 900 gigabytes per second, HBM bandwidth, total durations, and arithmetic intensities, etc. And the top dispatch also, which dispatch was the top one. As we saw that this is about on Grafana now, which is quite the same with the before. And now this is the roof line on the Grafana. It's a bit different, but now we have chosen kernel. So basically, I'm sorry, this is one kernel. But if I go back to the Grafana from here, I can select for which kernel to visualize data and do roof line analysis. So this is also really nice. Okay, so this one is close to the HBM bandwidth, but it probably could be improved in some aspects. Wavefront and compute unit. Here you see the wavefronts and the wavefront runtime statistics. Okay, kernel time, instructions per wavefront, wave cycles, etc. And here's the instruction mix, branch, VLU vector, etc. And yeah, operations, integer32, etc. So it does really huge analysis on your kernels. Instruction cache bandwidth only 4%, but cache hit 97, which means that usually the stuff that I'm asking is in the cache. And also here's instruction cache, and here's the L1 data cache. And also there's a L1 data, vector L1 data cache. If its buffer is coalescing, that's important. Cache utilization, cache bandwidth, and cache hit in this case. So you see here there is space for some improvements. That's quite really good to know. And this is L2 cache, L2 utilization, again 65% and a bit less. And you see, I want to just show you that you see a lot of numbers that sometimes is complicated to understand and read. That's why we try to set some documentation to improve the situation. You see HBM style, so there was a style on HBM stuff, some short delay. And also there's a L2 cache per channel. This is quite interesting, the L2 cache hit rate. Okay, so here it's like 16, if I'm correct, yeah, 16 channels. And for the L1 to L2 read request, L1 to L2 write request per wave, and L1 to L2 write request. Yes, so you can see a lot of information about also the interaction between L1 and L2. Yes, overall, I want to show you this part, and we should we'll take questions one moment, and we should go to exercise then. So we are in the OmniTools exercises, which means we are here. The fun thing that I think the OmniTools indeed had a problem with ROCm 5.3 here, but let's see that. Yeah, I think I will load directly. Let's see. Yeah, I have already GPU. I will copy the V copy here, and probably I need to do also clear the architecture. Oops. So now I'm going to run the vcopy with OmniPerf, I hope so, without any hint how many times to. So now you see, it's really small duration, but if you can see different metrics running now. Here you can see different metrics. And also here is the roofline calculation. So in the roofline calculation, you see, it starts running some micro benchmarks inside to see the empirical peak, right? Now this is fast because the roofline will be always like that, but the application is fast because it's quite small, right? We didn't want to, yes. So you see here, I don't know if I have already, okay. So here you see that, and I can, yeah, don't go directly here. I can do this. Now this, imagine, well, this is a bit small. It took some seconds. And if I open, again, top kernel, called once, the duration of the time, system information is also important at this moment, speed of light, you see here. Instruction cache hit rate is good. You can see command processor, GPU busy, other stuff, utilization, etc. So that's why I'm saying it's a lot of data that I don't want to read to you or to present to you because it's a lot of information. So to my opinion, you need to check which metrics are more interested, especially for your application, and seeing from this aspect where you should focus. So, and you see here, FMA arithmetic instruction mix, pipeline stats, LDS, not so much. So that's all, not so much stuff. Now, one moment to see exactly what I'll do here. If you want to say like that, I want only the 7.1.2 block, you will see this. So it was much faster, but you need to know what you want and why, of course, right? So now let me see how to do that. Workloads. Okay. So what I'm doing, I will download it. Let's hope it will work. Oops. Yeah, typo, sorry. So I hope. What? Wow. That's interesting. Okay, maybe I have it already. Let me see, maybe, okay, I have it already. This happened, I don't know what happened now. Anyway, the instruction that I have here in the page, let me see, because maybe, something is still slow. I'm sorry, something is really stuck. For some reason, it's not in my path yet. Ah, it is in path. So you see here, they did the analysis and it tells me, go to this web page, okay? And one moment, so I have to go there. And this is working because my web page now loads. Let me stop sharing here and start sharing the web page. So as you see, wait, something from Zoom is hiding. Okay, as you see here, I open the web page. I can see the memory. I can see the roofline. Okay, yes. Here, if I remember correct, something with the roofline is some values are zeros and don't appear here. And I can see what I presented to you as images, screenshots, I mean. And basically you go here in the menu, it's a roofline to go here. Or I think some stuff though are missing here though. This is little information. You can select kernel, but of course you have only one kernel. So if you have many kernels, you can select to visualize which kernel you want, which is of course important. So you see that even with the small data, yeah, because I have one moment. Sorry about this. So maybe this was an execution with less data, that's why it's missing some stuff. Yeah, I'm not supposed. Yeah, some stuff is missing. If I go to VPN, you can see much more information. Here they have appeared, as you can see here. The command processors, shader, and you can see here the graphs, right? So the one way is the standalone GUI. The other is Grafana. Grafana, you need to be like a server. It's not really a server. But the Grafana also has some extra, I think, graphics that standalone GUI is not the same. But for something fast, to check something like, you know, so a roofline or something, is really nice. Now, just to mention something though, so I'm just continuing to see here all the web page how it is. So it's a lot of data, right? This is for one kernel now. So imagine the application has 10, 20 kernels, and you have to so it's a lot for. Now here, for example, Del2 cache, I saw you before from Grafana. It's a nice graphics, right? From here, okay, you can see, but with the graphics is better. This is the truth. But if you are like in a hackathon or something, I believe that this is a really nice option to have. Now I wanted to show you something else that I forgot to comment, but so I'm here and I'll say so here that's only roofline. skips everything else. So it runs. So what I want to show you here, probably I will not download it now. This is the PDF with the roof line. So let's say before you go to the GUI, etc., and I don't know if this example is good for roofline. Before you go to GUI, etc., you have a PDF with a roofline there, and you can just see and say, "Oh, this change in the code maybe is not good, and let's try something else," for example. So it's also quite nice. Although we promote the GUIs, right? The Grafana, I suppose, first, and then standalone GUI. I think that was kind of all I had. So when I say the instructions open the web page, I follow always the instruction that it gives you, right? Because the IP changes can be different. Okay. So here it gives you this, okay, or this, something like that. Yeah, so that was all I had.
Okay, we had some questions earlier on the first day about how to report issues. And the recommendation I got from the team is for best tracking of issues, report to your primary site. And that will give you some visibility on the resolution of the issues. So that could be Lumi or KTH. If you do not have a site, you can contact one of us. And we will get it into the reporting pathway, but it may not be as visible to you. Research projects, OmniTrace, OmniPerf are tracking GitHub issues. So you could actually report them directly there or through this site reporting mechanism. Does that sound right, George?
Yes, correct.
The Siemens compiler, it's still in development, so we have a contract with them. So if you report them to the AMD team, they will be passed on to Siemens. Once the code gets upstreamed into the GCC, it will be through the regular GCC pathways. If you need help or you don't have a site to report, you can pass it on to one of us through any mechanism that you have to contact some of our training staff, and we will get it in the proper reporting. It may not be visible to you through that pathway, although we'll try and get back to you. Does that sound right, George?
Yeah, yes, absolutely.
And I do want to note some additional resources. There's a new blog that's out called Lab Notes that's on GPU Open. They have a finite difference method blog post they have just posted on stencil kind of code. Part 1 has been released, and there'll be a part 2, 3, and maybe 4. There is a blog on matrix cores and how to use them. So you might want to keep an eye on those lab notes being published there. We're releasing it on a 2 to 4 week cadence. And I think that'd be very helpful for special articles online on how to use the hardware and optimize for it. There are developer resources at developeramd.com. There's videos and other resources. We hope to supplement those in the future. The official ROCm documentation is at docs.amd.com. It's actually pretty good, though it can be hard to find information in there. They are also rapidly improving it, and there are some things that are not properly documented. If you have issues with documentation, they can be reported too. We're trying to get that quality up. Quick start guides at Oak Ridge. And Thor says he's going to have a site from this training that he's going to host that should be equally as good. So you might check those sites. Infinity Hub has a lot of popular applications. And then we do have the cloud resources for trying out AMD systems. If you want to continue these exercises, go to this acp.amd.com site, and in the upper right corner, you can put in a request for an account. That would allow you to experiment with things. It is not a general computing resource to run a bunch of jobs. It's fairly small. We also have an accelerator cloud in Plano, Texas, and it's not at the same level of quality right now, but it does have some resources, and we hope to upgrade that here in the near future. Do you want to add anything, George, to these?
Oh, it's really good.
Yeah. Any questions on these resources?